All right, let's go ahead and get started. So, how's midterm? Good, bad, bleh. Okay. Hopefully, everybody recognized that you were bright enough to ask me to solve problem 3 on the midterm twice during the review session. My guess is probably the average score on this exam is going to be somewhere in the neighborhood of 27 plus or minus 1 out of 40, which is about 7 out of 10 for each of the problems. People tend to, basically lots of little mistakes because it's an exam situation and that's just what happens. But generally, the aim was to make an exam that was slightly easier than I would usually do, partly because the last homework in particular was harder than I wanted it to be in the end. We'll see how it goes. We're hoping that we'll have at least most of the exam graded by the end of next week, which still leaves, I believe, 1 full week before the drop deadline, which is the only reason why we have the exam where we do. If people have any questions or concerns, I'm hoping to post the solutions. I wrote the solutions to everything except the extra credit problem while you were taking the exam. But I haven't had the time to write down the extra credit things. But I'm expecting those to be up tomorrow morning sometime. So please discuss the exam on Piazza or in office hours, or feel free to ask any of us questions. As promised, there is another homework up on the website, which is due next Tuesday, which I believe is likely to be known as Trump Day. Super Tuesday. I couldn't figure out how to actually make any of the problems about politics without offending somebody, so I figured it was better not to try. Again, there are only 2 questions here. One of them is, I think the number 1 I think is actually conceptually a little bit harder than number 2. Number 2 is mostly an exercise in understanding the definitions and being able to do a little bit of probability calculation. Okay. Any other logistical questions or administrative questions? Okay, great. So we've got 2 more lectures in the schedule to talking about randomized algorithms. And I wanted to present a few things that are a little bit more advanced or interesting than just standard hash tables, but things that actually might end up being useful. Right? So most of what I want you to take away from the lecture today, and probably even to a bigger extent the lecture on Tuesday, is the algorithms themselves, which are relatively simple, and then there's a somewhat complicated analysis that explains how they work. And then keep in mind that everything I'm showing you is kind of the initial example of the kind of thing I'm going to show you, and that they're more complicated variants depending on what you want to do with them. But one of the things that I want to specifically talk about today is randomized algorithms where there's a certain probability of error. All of the algorithms and the data structures that we've seen so far are guaranteed to always, 100% of the time, return the right answer. It's just that because of the randomization, we can make some reasonably strong claims about how fast the algorithm is most of the time, but we're really, we're going to hang on to correctness as, no, it really has to be exactly the right answer all the time. When I ask the hash table whether this thing is here, when it says yes, it's because it's actually there, and when it says no, it's because it's actually not. But it turns out that there are interesting practical applications where it's okay to be wrong part of the time as long as you can control the way that you're wrong and as long as you can make some claims about how often you're wrong. So some people distinguish between two types of randomized algorithms. There's a so-called Las Vegas algorithm, and there's a so-called Monte Carlo algorithm. So a Monte Carlo algorithm is always fast, whereas a Las Vegas algorithm is always correct. Correctness here might mean if it's a yes-no question, it always gives you the right bit. Correctness here might mean I'm aiming for an optimal solution of some kind. Like I want to compute the edit distance, and I really want the exact distance. Whereas a Monte Carlo algorithm might give you an estimate of the edit distance that's not necessarily the exact value, but because it computes it more quickly, maybe that estimate is still useful. And now it's probably fast. It's always fast, and it's probably correct, or at least probably good in a provable sense, right? Monte Carlo algorithms are actually older. So initially, Monte Carlo algorithms were developed as a way of doing numerical integration. I want to compute the very crudely, I have some blob, and I want to compute the area of this blob. Maybe the blob has a hole in it. Okay. The way the crudest level of Monte Carlo integration works is I consider some box that contains this thing, and I say, okay, let me normalize so that the area of this bounding box is 1, and then I'm going to throw random points into this box. Now, because I've normalized the area of the box to be 1, the area of the blob is exactly the probability that a point will land in the blob if I throw a random point in the box. Okay, so if I normalize this to area equals 1, then here the probability that a random point is inside this blob is exactly the area of the blob. So here's this blob B. All right, so I will throw random points into my area. I'll somehow check whether the point lies inside the blob, and I'll keep track of the frequency that points are good versus the points are bad. And after I've done this enough times, I will say my estimate of the area is the fraction of points that landed inside the blob. Now, the speed of the algorithm is just determined by how many samples you take. And things like Chebyshev's inequality and Chernoff bounds will actually imply that with high probability, the estimate that you get of the area is very close to the actual area. You have to be a little bit more careful. There's some subtleties that have to do with the shape of the boundary, but there's some assumptions that you have to make about how nice the blob is in order to get these guarantees. But the basic idea is that if I just fix the number of samples, so it's always fast, I can derive probabilistic quality guarantees on the answer that I get from the estimate. Okay. So the estimated area is the fraction of samples inside the blob. This goes back to the 1890s. This is really old. In fact, some of these experiments that look, probabilistic experiments that look like this actually date back to the 1700s, if I'm really being honest. Las Vegas algorithms were a relatively recent invention. These are probably first in any form discussed in the 1950s and in any reasonable modern form in the 1970s. And so people came up with, Monte Carlo because, you're gambling, it's random, and everybody knows that there's a nice casino in Monte Carlo, even in the 1800s. In the 1970s, of course, the center of gambling moved to Las Vegas. And just to distinguish, they came up with this terminology. Modern algorithm designers generally don't use this terminology because if there's an error, probability of error, we just say so. And if there's a distribution versus worst case guarantee on the running time, we just say so. Right? But you might run across these terms in other contexts. So in particular, I'm going to be looking, for this lecture at things that are Monte Carlo algorithms rather than Las Vegas algorithms. And in general, for the simplest kind of Monte Carlo algorithm, I'm going to imagine having some sort of error rate or error probability, which I'm going to denote by delta. This is sometimes also called, in statistical terms, is sort of a confidence 1 minus delta. The idea is that the probability of getting the wrong answer or the probability of getting a bad answer, depending on context, is at most going to be delta. And I want to figure out what the appropriate parameters of the algorithm or data structure will give me an error rate of this form. When I say the algorithm is correct with high probability, that means this error rate is some inverse polynomial, just like when we say the algorithm runs fast with high probability. But again, for practical settings, it's not necessarily important for this to be quite that low. In fact, for the kinds of things that I'm going to be talking about today, generally you should think of delta as being some very, very small constant, like 1 out of a million. Okay? Just in terms of the kinds of engineering applications that we would use these data structures for. Okay? So what I'm going to start with, the first of the two things that I'm going to talk about, is exactly the context where we would use hash tables. I have a set of objects from some universe, and new objects are going to be inserted into this set over time. And at various times, I need to be able to ask, is this element in the set? Right? So I need to be able to handle insertions, and I need to be able to handle queries with a little bit more work based on the kinds of things I'm going to talk about. You can also handle deletions, but it's not going to be quite as simple. But I'm going to allow the query to have some probability of giving you the wrong answer. Okay? And in particular, the setting that I'm interested in, this is one-sided error. Okay, so the idea is that if X is in the set, then the algorithm always says yes. And if the item S is not in the set, then the algorithm is going to say no with probability at least 1 minus delta, and it will say there's some small probability that it'll say yes. So in this context, the error probability is a false positive rate. You'll never get false negatives. You'll occasionally get false positives. And a data structure that has this form is sometimes referred to as a filter. Right? And the idea is that if I have some more complicated data structure that I want to ask questions about the data, I have data that I want to retrieve, secondary values, or this is the index into some really more complicated database. What I'd like to be able to do is quickly realize that with reasonable probability that this item that I'm asked about is completely irrelevant. So, for example, internet backbone. A packet comes down the line, and it says, this is the source IP address for this packet. I might apply a filter to say, is this coming from some malicious site? Right? Now, in this case, what I really want to ask is, does this come from a site that I know to be trustworthy, that I know to be reasonable? If it's in the set of reasonable sites that behave well, I really want to say yes. If it comes from some sort of botnet, that even a botnet that I know about, most of the time I want to say no. But if I let 1 out of a million bad packets through, it's not so horrible. Okay. Or another version of this is I want to know if well, let me just stick with the one example for now, rather than trying to make something up. Okay. All right. So, what I'm gonna the version of this that I'm going to talk about was first developed in the 1950s by someone named Calvin Moores. This was known as Sato Coding. And it was used as a way of encoding, so this is 1957, 60 years ago. Basically, it was used for things equivalent to library card catalogs. It was first used, actually, in chemistry, but then it was used in a whole bunch of other things. And it was relatively popular in libraries, became popular in the Census Bureau back before computers existed. And so the idea is that you have a card for each item in your database, and the card has a few features attached to it. So this is a patent that is about, it's a selective device, it has some photoelectric sensing, it's got a camera built in, it counts things. And later somebody's going to come and say, find me all the patents that talk about cameras. So what the Sato coding idea is that for each of the possible descriptors, you come up with a set of random numbers. And then with a mechanical hole punch, you punch a notch into the top of the card at those locations. Then, if, for example, I want to find all the cards that have something to do with cameras, the code for cameras is 182934. I'll stick a needle through, the places where they don't have notches. In this case, it's done optically, but in many cases, it was done with an actual knitting needle or something equivalent. So there'd be holes here that you could stick the needle through. So I'm going to stick a needle through slot 1 and pull up. And any card that doesn't have a notch there will get removed. And then I'll stick a needle through hole 8, and I'll stick a needle through hole 29, and I'll stick a needle through hole 34. And I pull all of those needles up, and only cards that have those 4 notches will be left behind. Okay? This is also sometimes called an overlay code. There's a bunch of information theory stuff that was developed about it, but I will remind you that information theory was launched by Claude Shannon when he was a grad student at MIT in 1958. Calvin Moores was a master's student at MIT in 1957 when he came up with this, and he successfully launched a company to do this. The more modern version of this is called Bloom filter by totally different computer scientist named Burton Bloom in the 1970s, who had by 1970s everybody had forgotten about actually using physical cards with physical notches in them to store data. By the way, the idea of using notches in cards to do essentially database indexing dates back to Hollerith in the 1920s. Have you ever seen those like IBM cards? There may be some still floating around the world. The 80-column things with the little look like 1 by 2.5 rectangles at various places. Those cards were developed at IBM by Hollerith and others, and it ultimately dates back to the Jacquard looms in the mid 1800s, which were a pretty significant source of inspiration for Babbage when he was building his difference engine. So this idea of physical data structures is actually quite old. So it's a little disappointing that Bloom didn't know about it. So what's a Bloom filter? So a Bloom filter is an array of bits. All right, so I'm just going to have a big array from 0 to m-1 of bits. And initially, all of these bits are equal to 0. And I'm going to have k different hash functions, which, h sub I, from whatever my universe is to the indices from 0 to m-1. For purposes of analysis, unfortunately, I need to imagine that these are ideal random hash functions. This is just one of these unfortunate cases where theory hasn't caught up to practice. It works great in practice. It'd be nice if somebody could prove that you can make Bloom filters provably work with, say, only pairwise independent, only strongly universal, or you can make Bloom filters work if you use tabulation hashing, for example. This is an open question. And I will remind you of my standard course policy that if you publish something because of something you learned in this class, I'll give you an A+. Not that it'll matter because you'll have a paper. Okay. So I'm going to assume that this is an ideal random. These are ideal random and independent ideal random hash functions. And then if I want to insert a new item x into my Bloom filter, I do more or less the obvious thing. For I equals 1 to k, I take the bit at position given by the ith hash value and I set it equal to 1. Stick to my usual pseudocode notation here. And then if I want to do a membership query, anyone want to guess? All right, so for I gets 1 to k, if the bit at position I equals 0, I return false. And if I manage that all those bits are equal to 1, then I return true. Okay, there's the code. At this point, I'm reasonably confident that modulo the choice of hash function, you can implement this in about 10 seconds. This is really all there is to it, aside from the choices of the various parameters that go into building the data structure. What, given that you expect there to be n items in the data structure, how big should I make m, the size of the table? How big should I make k, the number of hash functions? And what kind of error probability delta should I expect given those parameters? Okay, so the analysis is really where everything happens. Okay. So let me start really simple in terms of doing the analysis. First of all, I'm going to observe that, again, this is probability over my choice of random hash functions. That, let me just ask, after I've inserted n items into the table, sorry, what am I thinking? All right, sorry, let me erase that for a second. Start over. First of all, the probability that hi of x is any particular value j is 1 over m. Okay, so the probability that insert x does not set b sub j equal to 1, this is going to be, well, I've got k different hash functions, and they're all independent. And the probability that any one of those hash functions doesn't return the value j is 1 minus 1 over m. Okay? And so this means that after I've inserted, after n inserts, the probability that a particular location is equal to 0 is going to be equal to 1 minus 1 over m to the k to the n. Because again, I'm assuming that here, to simplify things, I'm assuming I'm inserting n different values. The hash values for any two items are completely independent from each other. So I can just multiply the probabilities over all x in my data set together. Right. Here's where I'm using ideal randomness. Okay. Now, by the world's most useful inequality, e to the x is bigger than 1 plus x. This is at most e to the minus kn over m. And I'm going to take this to be, I'm going to call this parameter p. P is my estimate of the probability, after I've initialized the Bloom filter, of a particular cell in the table of being equal to 0. Okay, so, or in other words, P is my estimate of the proportion of the bit of the Bloom filter that is equal to 0. Okay? Right, so this is just an estimate for this probability. Okay? So now let me ask, what's the probability of getting a false positive? Right, so I'm going to come up with a new item y that's not in the set and ask, what's the probability that all of the bits that y hashes to come up 1? Well, notice first of all, if y is in the set, then this member subroutine will return true. Right? So this is why I said false positives only. But there is a small chance that I might, just by accident, hit the first bit of x and the second bit of q and the third bit of omega and the 17th bit of aleph, and instead of actually finding the item y that I want. Okay, so the probability is basically going to be 1 minus p to the k. Remember, p is the probability that a particular bit in the table is equal to 0. And the way the membership algorithm works is it probes k random bits. So the probability that any one of those bits is equal to 1 is 1 minus p. And because I'm probing these things independently, I take this to the power of k. I'm waving my hands a little bit here because the probabilities, I'm acting as though I've got k completely independent variables here. But in fact, even if I assume that the hash functions are independent, if I probe k random places and I notice that the first one I land on a 1, that actually makes it slightly less likely that other places in the table will be equal to 1. Which means formally, these things that I'm multiplying together, I shouldn't be doing because it's not independent, right? The more formal way of saying this is that my estimate for p is with very high probability within a very small window of this value. And no matter what the value is, once I fix the fraction of 0 bits in the table, then I can do this. So in actuality, this is a slight underestimate. In practice, by roughly 3 or 4%. Yeah.
On top of that, would it also be possible where multiple hash functions map the same depth?
Yes, but so it's possible that the different hash values could all be equal. But I'm already sort of taking that into account. If I really had, is this right? If the various probabilities, if the various things were actually independent, then doing the I'm doing sampling with replacement rather than sampling without. And I think, again, this will only make a small difference. Right? We actually had the same issue up there when we were inserting. When we insert, we don't insist on choosing k distinct values. We just take whatever k values the hash functions give us. Yeah.
So if it was ideal random, would that be the case?
No, I mean, this sort of is on top of the hash values are ideal random. I'm even with ideal randomness, I'm waving my hands. Okay. But I'm waving my hands in a way that only makes trivial differences with the actual truth. And going through the actual formalities would not be enlightening.
Which part actually make it sort of again?
I'm sorry?
Which part make it sort of?
So here I'm saying, so the probability of a false positive is the probability that the first bit is a 1, and the second bit is a 1, and the third bit is a 1, and blah, blah, and the kth bit is a 1, even though the item I'm looking for is not in the data set.
Yeah.
The problem is that once I probe and I see that the first bit is a 1, it's actually slightly more likely that the next bit I look at will be a 0.
Why? But you prove this.
Because I know something about the fraction of 1s. So if I observe a 1 here,
yeah,
and I know that there are only 100 1s,
but the next
then
time,
instead of having a 100 over n chance of seeing a 1 here, I now have a 99 over m minus 1
but
chance.
you sample with all the replacement. So
I-
you could land at that point again, right?
Yes, it could, in which case I know that it's a 1. It's subtle, and I don't really claim to be able to say anything other than if you try to prove that these random variables are independent, you will fail. They're not independent, even though it looks like they should be. And people have actually gone through and done the analysis correctly. And again, the difference here between reality and what this predicts is, in practice, about 2 or 3%. So we'll let it slide. Okay. Okay. So and then I can, again, just by plugging in p here, I can write this as some complicated expression involving e's and m's and n's. Right. So remember, this is delta. Okay. So given if I fix the number of items that I'm going to put in the table, and I fix the size of the table, and I fix the number of hash functions, this tells me within a few percent what the false positive rate is. Yeah. So what I mean is, you should imagine that I have k tables full of random numbers, each table the size of the universe. And when I get x, the first hash value is x's random number in the first table. Right? I mean, when I get x, I roll an m-sided die, and that's h1, and I roll an m-sided die, and that's h2. This is not anything that you can do in practice. Right. Right. And the reason I'm assuming ideal randomness is not because it's realistic, but because I can prove something. Right. And again, experimental analysis of this, if you actually implement this and compare the experimental performance versus what the theory predicts, it's very, very close. And the problem is not with the ideal randomness. The problem is actually with this independence down here, even when you have ideal randomness. So, a couple of things to notice here. It may not be obvious, because there's lots of minus signs floating around. But if I increase n, if I put more things into the Bloom filter, well, there's 1, 2 minuses in front of the n. So as I increase n, delta is going to get bigger. This is sort of obvious. The more things I have in the table, the more likely I am to make a mistake because there are more bits set to 1. On the other hand, if I make the table bigger but keep the other parameters fixed, the false positive rate will go down. Again, this makes sense because as I make the table bigger but I have the same number of items and the same number of hash tables, you expect the fraction of 1 bits to go down. What's a bit harder to figure out is what happens with k. Because, well, it's just harder to figure out. And the truth is that there is, if I fix the size of my table and the number of things I want to put into it, if I knew those in advance, then there is a best possible value of k. Okay. This function delta, if I keep everything else fixed and I vary k, actually has a single global minimum. And so to figure that out, I'll take the log of both sides. Okay. This is log of 1 minus p to the k. That means that's k log 1 minus p. At this point, I will, instead of expanding p as a function of the other parameters, I'll expand k as a function of nm and p, or mn and k. And that comes out to be minus m over n log p, log 1 minus p. Okay, so k turns into this. And now if I look at this expression, first of all, if any of you are ECE majors, you might have done in the information theory, this might have already shown, this kind of thing might have already shown up. But one thing you'll notice is there's a symmetry here. I've taken the product of these two concave functions. Because there's a negation here, I want to maximize this product. That's going to happen when p and 1 minus p are equal. Right? So this is, the maximum value happens when p is equal to 1/2. And then if I plug that back in up here, that means k is going to be m over n times the natural log of 2. Okay, so math. But in the end, what you end up finding when you do this analysis is what you want to aim for is the right number of hash functions so that after you've built the Bloom filter, half of the bits are zeros and half of the bits are ones. If you use fewer hash functions, you'll have fewer ones. But somehow, because you're making fewer probes, when you do membership queries, the probability of a false positive will go up. If you use more hash functions, you'll have more ones, and so it's more likely that you'll get a false positive that way. So if I fixed m and n, I just multiply by this number, which is about 0.7. I know it's not actually an integer, so k has to be an integer, so you have to do some rounding. But, yeah.
Is k the number of hash functions?
K is the number of hash functions. That's right. Okay. And so if I plug this back into delta, what I'm going to get is well, p is 1/2, or 1 minus p is 1/2. To the k, that's m over n log 2. This comes out to be about 0.6185 to the m over n. In other words, as long as m over n is a constant, then I get a constant failure probability. So if I want to build a Bloom filter for 1 million things, I really need to imagine allocating at least, if I allocate 1 million bits, my false positive rate is going to be 60%, which is not great. Another way of saying this is that now if I want to fix n and fix delta, so I have a certain number of things that I'm going to put in a Bloom filter, and I want to guarantee a certain error probability, then I can turn this around and say I should set m to be approximately the binary log of 1 over delta divided by the natural log of 2 times n. Okay, or to say this a little bit more succinctly, order n times log of 1 over delta. Okay. So if, for example, I wanted to guarantee no errors with high probability, if I wanted an error probability of 1 over n, the only way to do that is using log of 1 over delta hash functions, which means I'm going to be computing log n roughly different bits and spending log n time doing the probes, which is not great. On the other hand, if I throw in just throw down a couple of examples. Okay, so if I want delta to be 1%, then what I should use is 10n bits and 7 hash functions. If I want delta to be, so if I turn this around and I set m to be 32n, right? I'm willing to allocate a complete 32-bit integer for every item in my data set, which is a completely reasonable thing for most data structures. Then this is going to imply that if I use 22 hash functions, then my error rate is just a little bit over 2 times 10 to the minus 7. Roughly 1 out of 5 million. Right, so if I'm willing to allocate 32 bits to each item, I can get an error rate of 1 out of 5, 1 out of 5 million, just by using 22 hash functions. And this is if I'm willing to settle for a 1% error rate, then I only need to allocate 10 bits per item, which is considerably less than what you would use for any other reasonable data structure. Yes?
That best probability delta. Is that
Right.
read guarantees?
Sorry?
If you were reading that left to right, would it say
It says, if I set the size of the table to be log base 2 of 1 over delta divided by natural log of 2 times the number of items that I want to put into the data structure, then the error probability for the resulting Bloom filter is at most delta. Yeah?
why you set k to be equal to minus
Oh, so notice, here's the definition of P. P is equal to e to the minus kn over m. Now, solve for k. That's all it is. I'm not, I realize this is a little bit hard to follow because I've got only one Greek letter, but I've got K, N, M, P, and I guess if you're really counting E, and it's hard to keep track of what all these letters are. For now, again, as I said, the thing I want you to take away from this is not so much the details of the analysis, but the general idea of how Bloom filters work. I'm sorry?
You might cut out.
I might cut out. Thank you. And there are no batteries. Lovely. I'm going to steal from the other mic. If I can. Okay. Looks like it might work. So I've only got one bar, but I've only got 35 minutes, so we'll risk it. Or 25 minutes, we'll risk it. Question?
Yeah, I'm trying to see how this compares to ordinary hash functions. So ordinary hash functions, you use it as a set, you get one query time and one full n space.
Right, so so how does this compare to a normal hash table? So with a normal hash table, first of all, you probe into constant number of places. You either get the right answer or you don't. The problem with the hash tables is you have to deal with collisions. You actually have to store the data in the hash table, not just a bit that says whether it's there or not. Okay, so Bloom filters are more compact at the expense of a small probability of error. And by construction, the query into a Bloom filter takes, log of 1 over delta time. Right? So if I set delta, right, if I want my delta to be 1 over a million, k is going to be about 20. I need to probe 20 bits in my table. And the algorithm is incredibly simple, which means, among other things, it's embarrassingly parallel. Right? So if I have a multi-threaded machine, I don't have to do these actually in a for loop. I can literally just say, okay, you 8 processors go probe 8 bits. Okay, you go probe 8 more bits. And in particular, if I want to build this in hardware, this is ridiculously simple. Modulo the construction of the hash tables. That's not terribly difficult. The hash functions, excuse me. Whereas if I really want to implement, linear probing or cuckoo hashing or something else in hardware or using parallelism, it's much more difficult because the algorithms are much more involved. Yeah.
So in practice, for a hash table, we have key value pairs, but it seems
Right.
like we're ignoring the value. And just focusing on
Yes, that's an excellent point. So normally for hash tables, you're not just looking up whether the item is in the set, but you have some value associated with that key that you're looking up. And for Bloom filters, the other thing that you're losing is you can't associate a value with the set. This is just sanity check, is it there? And if the answer is no, then you know that's the truth. And if the answer is yes, then you're reasonably confident that it's the truth. And now you can do something much more involved and much more expensive, but because you did this sanity check first, you know that you're not going to be doing that more expensive computation on something that doesn't really matter. Right? Yeah.
Can you explain again how you apply the world's most useful inequality? Okay, that step.
Right here, going from 1 minus 1 over m
Yeah.
to e to the 1 over m, e to the minus 1 over m.
Yeah.
Here, x is minus 1 over m. Going from here to here.
Oh, okay, I see. And then how were you able to, since p previously equaled the thing on the left side of the inequality, it seems like you sort of treated that as an equality and then treated p as...
Right, so as long as, the other thing is, as long as x is small, this inequality is very, very close to being an equality. Right, so you can generally write something like, if x is small enough, you could write this as, for example, that, or 1 plus x, x times 1.1, or there's lots of approximate versions going the other way. In the limit, as x goes to 0, the ratio between these two things goes to 1. And the one way to remember that this inequality is that these are just the first two terms in the Taylor series expansion of e to the x. But the way that I actually remember it is here's a graph of e to the x, and here is a graph of 1 plus x. It's just the tangent line. Okay, so any other questions about this? Now, I'll mention in passing, there are versions of Bloom filters that allow you to do deletions. But when you do deletions, you necessarily introduce the small false negative rate as well. Because you might accidentally delete something that wasn't there, or you might, there's a possibility that you'll see zeros because somebody else deleted your bits. Okay, but the analysis is very similar. There are also versions where you can associate key value pairs, like hash tables. But now there's a small probability that when you say, go look up this value, instead of getting a sensible value, you'll just get garbage. So if you look up an item that's not in your hash table, most of the time it will say, I've never seen that thing before in my life, but occasionally it will give you some data that is meaningless. And so you have to be able to deal with that nonsense result. On the other hand, if you look up a value that you have stored in the table, again, for these key value things, there'll be a small probability that you won't get it back because other people have overwritten your bits. But the general idea is that these data structures generally are simpler and more compact than standard hash tables, and you pay for that additional simplicity and compactness with the error probabilities. Okay. So that was thing one. There are lots of applications of these things that are actually quite common in information retrieval, which is where they were launched, but also in systems and networking. There's a lovely survey by Mike Mitzenmacher and Andre Broder. Mitzenmacher was recently the Harvard's equivalent of department chair for their Department of Computer Science. Andre Broder was the architect of the Alta Vista search engine, which later got sucked into Yahoo. It was sort of the main competitor for Google. And Google stole a lot of their ideas. So a lot of Google's algorithms for indexing web pages also rely on variants of Bloom filters. Okay. So the other context I want to think about is what are called streaming algorithms. So I want to imagine that I have a stream of data flowing by very quickly, and I've got some sort of device that's watching this stream. The obvious example to use here is either one of the connections on the internet backbone, or search queries at google.com. Lots of data just flying at you, right? And you need to be able to compute something interesting about this data, and you need to be able to do it very quickly. Every time a new item comes up, you need a simple algorithm that processes that item and then forgets it. So in particular, I want to imagine, for purposes of this, that there's very low, memory, very little RAM sitting in this device that's monitoring the stream, and I have lots of data flowing by. And I still want to be able to compute something interesting. So the particular problem that I want to show you a solution for is how many times have I seen item X? Okay, so if I'm looking at the internet backbone, how many times have I tried to route a packet to a particular IP address? I do not have enough memory to store a table of all IP addresses and the number of times I've seen them. Or how many times has somebody gone to google.com and looked up mesothelioma? Given the price of the ad word for mesothelioma, a lot. It's a cancer that you get by breathing asbestos fibers. They're active lawsuits that have been going on for decades. So lawyers are willing to pay a lot for putting an ad on that word. And it's not at all obvious that you can do anything, really. Right? So I'm going to do something that is somewhat reminiscent of a Bloom filter. In fact, it sort of evolved out of Bloom filters, called a count min sketch. So this is something that was, I'm trying to remember who actually developed this. No, I don't have the names written down. I think this came out sometime in the early 1990s. A count min sketch is a W by D array of bits, which you should read as width and depth. Right? And I really want to think of this as D W bit vectors. And I should also imagine that I have D hash functions. H sub I from whatever my universe is to the width of the table. Interestingly, now I only require these to be universal. I don't require ideal randomness here. All the analysis only relies on thinking about pairwise collisions. So any of the hash functions that you saw before the midterm will work here. Okay. Now, sorry, I made one mistake here. I'm not going to store integers in the table. I'm sorry, I'm not going to store bits in the table. I'm going to store integers. I'm going to store counters. Okay. Now, initially, all these items are 0. When I see a value x, what I'm going to do is, for every layer of my table, I'm going to take my array, which I'll call count, at layer I, at position hi of x, and I'll increment that counter. That's it. That's the whole. I saw x. Okay. And now I want to be able to estimate, given the values that are stored there in the table, I want to estimate how many times have I seen x. Now, I can look at each of the counts corresponding to x. So a particular x comes by, and I'll increment, some of these counters. And so what I could do, if I look at any particular one of those, the number stored in that particular slot, count of I, h sub I of x, is at least the number of times that I've seen x. So I have a lower bound on the frequency that x has been seen. So what do I actually return? I'm going to return the minimum over all I.
Excuse me.
Yes?
Do you mean the highest bound, not the lowest bound?
I have a lower bound, meaning, sorry, I have an upper bound. You're right. Each of those is an upper bound. Each of those is an overestimate of the true frequency. So I'm going to take the smallest overestimate as my real estimate. Okay? So, yeah, I really put this in a for loop with an infinity and a minimum, but you get the idea. Okay, so each of those items in the position given by the ith hash function in the ith row is at least the true count, and I'm going to take the one that out of those counts that is the smallest. Okay. And now what I want to claim is that with appropriate choices, if we choose W and D correctly, the probability that my estimate is bigger than the true frequency of x, the true number of times I've seen x, plus epsilon times the number of times that I processed is at most delta. Okay, this number of times that I processed, this is the total number of items that I've seen in the stream over all time. Okay, so I think just to be consistent with my notes, I'm going to refer to this as n. This is the total length of the stream, well, so far. Okay? So this is a pretty weak guarantee for items that are infrequent. Right? So what this says is that after I've seen 1 billion items, I want to be able to guarantee that anything that has gone by more than 1 million times, my estimate should not be more than 2 million. Okay, as long as I'm interested in how many times I've seen really popular things, I'm willing to tolerate a small multiplicative error. But there's sort of this inevitable noise that essentially, if I set epsilon to be 0.01, right, I'm just completely confused about 1% of the things I saw, and I think, how many times have I seen Kanye West? Oh, you look like Kanye West. You look like Kanye West. 1% of you, I think, is Kanye West. Okay, and as long as I see Kanye West more than 10% of the time, that doesn't matter so much. Okay. So, what do I need? I need to set these bounds correctly. What do I need to do? What are the actual correct values? These turn out to be W is about, well, I need a ceiling because it has to be an estimate. This is E over epsilon. This is E, Euler's number, 2.71828, over epsilon, the amount of error in my estimate that I'm willing to tolerate. And on the other hand, what do I want to make D? This should be the ceiling of natural log of 1 over delta. So in a lot of these kinds of Monte Carlo algorithms where I want a confidence interval of 1 minus delta, log of 1 over the failure probability shows up naturally as a parameter in either the space bound or the running time or both. Okay. What's more interesting here is you'll notice if I want my error, my estimate to be, say, I'm confused about 1% of the stuff, that means that this picture is actually a little bit inaccurate, because if epsilon is a constant, say 1 over 100, this is 272, not 272n, just 272. Right? It's a constant. Yeah.
So you don't care if you slightly overestimate or grossly overestimate?
So I don't. So it's okay to overestimate, but the error that I'm tolerating is additive. Right? If I've seen a billion things, it's okay to overestimate by an additive error of a million. Right? I'm not controlling the multiplicative error, which is what I might really like to do. I'd like to say,
If you're a million and 1 over, it doesn't have this million of 1 or 100 million.
I'm sorry, say that again?
But if you're already greater than this frequency x plus epsilon n, it doesn't matter how much over it you are?
No, remember, this is the probability that an estimate is too large. The probability of getting a bad estimate is small.
Okay, but you're saying all bad estimates are equally bad?
Yeah. Once the estimate is bad, it's garbage. But the idea is that I want the probability of garbage to be smaller than delta. With the probability of garbage to be tiny. Now, with a little bit more care, you can arrange that worse garbage is less likely. But I'm not doing that analysis here. Okay. So in 5 minutes, I'm not sure that I can do the true justice to the analysis, but let me at least give you one piece of it. So let me write x sub I comma x. This is going to be the number of collisions with x in row I. And this means over all other items y that are not equal to x, how many times did y, the ith hash value of y agree with the ith hash value of x? Okay. So this is the sum over all y not equal to x of the indicator ith hash value of x equals the ith hash value of y times the true frequency of y, which means that if I want the expected number of these collisions, then I just put this probability here. And notice that, as usual, my randomness here that I'm taking the expectations over, this expectation is over my random choice of hash function. I'm not assuming that the data that I'm putting into the stream is random. The stream is arranged adversarially to screw me up. But because I have pairwise independent hash functions, I actually know what this probability is. It's 1 over m. And so I can write this, it's 1 over w. So I can write, say, altogether, this expectation is at most n over w. I've got... No, thank you. I've got n things, and each of them has at most the probability of 1 over w of a collision. Sorry, yes?
What tail
This isn't even a tail inequality. This is the definition of randomness. Ultimately, the analysis boils down to Markov.
Okay.
Only Markov. Right? I'm not even using Chebyshev here.
Yeah.
So now what you're actually asking for is what's the probability that this thing, the number of collisions that I get is bigger than epsilon times n? What's the probability that item x sees a lot of collisions at level I in the table? This is going to, by Markov's inequality, come out to 1 over w times epsilon. And so what's the probability that my estimate is too big? This is the same as the probability of this event happening for all I, and because these things are independent, this is going to come out to 1 over w epsilon to the d. And now if I just plug in those particular values of w and d, this is going to come out to be less than delta. Right. This is Markov's inequality. And that's it. So what this says is that as the stream of data goes by, I can at least get reasonably accurate counts of the most common things that I saw in the stream. Yeah?
What is epsilon?
Epsilon is the error that I'm willing to tolerate in my estimate. Okay. So as long as I'm looking at things that are reasonably frequent, I'm going to get a reasonably good estimate most of the time. Now there are other versions of this, other things you can do with stream processing. For example, you can figure out how many different things have I seen. Okay. I'm going to try to work that one into the homework. You can estimate what are the top 10 things that I've seen. Just tell me the 10 most frequent things that have flown by in the stream. And then, once you've got, basic stuff that tells me about, how often I see things that are common and what are the most common things and how frequent are they, there are other more complicated statistical tests that you can do on the stream. And keep in mind that if you're willing to tolerate, a 1% error only 1% of the time, that this is a data structure of constant size. Right? It's a 300 by 4 array of integers. Just pretty cool that you can actually do something with constant space and constant time. Yeah.
I don't know if I missed it. We haven't really talked about how built up this is. How the more data you have, you're gonna.
Isn't that interesting? The number. So the only place that the number of items you've seen shows up in the analysis at all is right there in the statement of what it means to be a bad estimate. Nothing about how big the data structure is, nothing about the running time. Depends on the size of the stream. Okay. Now, interestingly, there are techniques where I don't want the error bound to grow arbitrarily. So every so often, I just divide all my counters by 2. And now you have kind of a windowed estimate. How many times have I seen this item in the last 2 weeks? Right? And again, slightly different statistical guarantees.
It seems to me you have to store the value of x somewhere in order to estimate it later.
No. You tell me the value of x. I look at those bits in the hash table and I say, I think I've seen that 72 million times. And then I forget x.
But you may have x and y and z other values.
You're going to task me which x you're interested in. I am just going to store a table of counters.
Okay.
And the way that I know which x you want me to ask about is you tell me. Right? So, as I said, there are other versions of this where it says, maintain at all times an estimate of the top 10 things. And what that means is 99% of the time, the 20 things that I'm holding include the top 10 things.
That means I need to have a separate storage too.
No, but you may say, it just depends on the context that you're interested in. How many times have I gotten a packet from Google.com? Right. Okay. Thank you. Have a good weekend.